Homogeneity and inequalities. Homogeneity of functions. Let's consider a function Rn to R from n-dimensional Euclidean space to the real numbers. Definition. A function f Rn to R is positively homogeneous of degree k if the function of alpha v is the same as alpha to the k f of v for all scalars alpha greater than 0 and non-zero vectors v in Rn. Homogeneous functions are severely constrained. Suppose that we know the values of f for any vector on the unit sphere. Let v be in Rn be any non-zero vector, not necessarily on the unit sphere. We can find the value of f at v with homogeneity as f of v is the same as f of the norm of v over norm of v, which is equal to v to the k f of v over norm of v. Because v over norm of v has length 1, the value of f v over norm v is known, so we have derived the value of f of v. In fact, the function is uniquely and freely determined by its values on the unit sphere. Note that although the values of the function are constrained on each ray starting at the origin, this does not imply any relationship between function values on different rays. In particular, the function might still be highly discontinuous. Here are some examples of homogeneous functions. Let the two norm be Rn goes to 0 to infinity, not including infinity, be the usual Euclidean norm. Then the homogeneity property of the norm precisely says that the function is homogeneous of degree 1. In fact, the norm of alpha v2 is the square root of alpha squared v1 squared plus alpha squared n squared, which is the same as alpha norm of v2 for any alpha greater than or equal to 0. So we have a similar result for other norms in Euclidean space. For example, if we consider the 1 norm, the norm of alpha v is absolute value of alpha v1 plus absolute value of alpha v2 and so on, which is the same as alpha v, one norm of v. So the homogeneity degree is again 1. Any polynomial that is homogeneous of degree k is also homogeneous by our definition. In fact, we can define the polynomial p Rn to R by px1 through xn is equal to the sum of alpha, absolute value of alpha equal to k, c alpha x1 alpha 1 all the way to xn alpha n, where the sum is taken over n tuples alpha 1 to alpha n, such that each tuple, the jth tuple, is a non-negative integer, and absolute value of alpha is equal to alpha 1 plus alpha 2 plus alpha n is equal to k. Such tuples are called multi-indices. For example, p of x1, x2 is x1 squared plus 2x1 x2 plus x2 squared, is a homogeneous function of degree 2. Not all polynomials are homogeneous. In fact, qx is equal to x plus x squared is a polynomial of one variable which is not homogeneous. Homogeneity of inequalities. Homogeneity solves problems in the theory of inequalities by reducing complicated expressions to a form we can manipulate. To illustrate the technique, we will prove the Cauchy-Schwarz inequality for numbers x, y in Rn. The sum k is 1 through n of xk, yk is always less than or equal to the square root of xk squared from k1 through n times the square root of yj squared from j1 through n. Putting on our homogeneity thinking caps, we notice that each side of the equation is a homogeneous function of degree 1 in both of the vectors x and y. We therefore suspect that leveraging this homogeneity will make the inequality easier to prove. To this end, we will prove the inequality in 2 steps. We will establish the inequality given that the sum of xk squared is equal to the sum of yj squared is equal to 1. We will extend it to general x and y. Let's get started. We first need to show that the sum of xk, yk from k1 through n is less than or equal to 1. For all x and y in Rn such that the 2 norm of x is equal to the 2 norm of y is equal to 1, i.e. such that the sum of xk squared is equal to the sum of yj squared is equal to 1. To prove this, we recall that the square of any real number cannot be a negative integer. Therefore, xk minus yk squared is greater than or equal to 0 for each k. Expanding the square and rearranging, we see 2xk yk is less than or equal to xk squared plus yk squared. After adding all of the inequalities together, we apply our hypothesis. 2 sum of from k equal 1 through n of xk yk is less than or equal to k is equal to 1 of xk squared n plus yk squared from 1 through n is less than or equal to 2. Dividing by 2, we deduce that for k equal 1 through n, xk yk is less than or equal to 1 as required. Now we will show that this is sufficient to prove the inequality for all possible xy in Rn. The inequality is obvious for 0, x or y, so we can assume that both of the vectors are non-zero. If we write x tilde is equal to x over 2 norm of x and y tilde is equal to y over 2 norm of y, we can rearrange the left-hand side to get xk yk from k is 1 through n, the 2 norm of x times the 2 norm of y, sum of xk tilde yk tilde from k is equal to 1 through n. The theorem is true for unit length x and y, so it's less than or equal to 2 norm of x times 2 norm of y, which is the square root of xk squared from k equal 1 through n and yk squared from k equal 1 through n, as promised. This proof can be imitated to prove analogous results for infinite series and integrals. For example, given square integrable f and g, we have the integral of f of x, g of x dx is less than or equal to the square root of the integral of fx squared dx and the square root of gx squared dx. Although we decided to look at the Euclidean norm in this example, we could have just as easily chosen to require that the absolute value of x1 through xn is 1, or any other convenient scaling factor. The form we chose was tailored to the Cauchy-Schwarz inequality. And that's it for homogeneity and inequalities.